So, dear students, let us continue our discussion on electrostatic potential and capacitance. Today, we are going to discuss about connection of capacitors or combination of capacitors in parallel. Yesterday, we were discussing about the combination of capacitors in series, and we obtained the expression as 1 by Cs, the effective, is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So, today let us see how the combination gives rise to an effective capacitance when we connect them in parallel. Okay, in parallel. So, parallel connection basically means connecting all the capacitors end to end to a single battery. Okay, so end to end connection. So, now I will be taking only two capacitors. Okay, let me call this as capacitor C1 and this with the capacitance C2. Following. Now, these two has to be connected in parallel. Okay, parallel connection. See, these two are parallel to each other, right? The lines, and this was series, in series. This is how it goes. Okay, yesterday's discussion now was about series connection. So today it's about parallel connection. I'll connect these two capacitors to a battery. Okay. Now, okay, the heading is combination or parallel combination of capacitors. Okay. Right. So now we have two capacitors C1 and of capacitance C1 and C2 connected in parallel to a battery of potential difference V. Okay. Let V be the potential difference across the battery. So the same potential difference will be maintained across C2 and C1. Okay. So it's the same potential because they are connected in parallel. When we connect them in parallel, the potential difference remains the same for both of them. Okay. You will get to know when we discuss about current electricity there in detail. So now you take that. Okay. Potential difference remains same. V when you connect it in parallel. But the charge stored in each of these capacitors will be different, because see, when you have let me draw an effective capacitor. So let this be the effective capacitor, a single capacitor which will give the same effect or which can store the same amount of charge, not same amount of charge, which will give us the same effect when we have C1 and C2 connected in parallel. Okay, this is effective capacitor. So in the last derivation, effective capacitor was named as Cs because the capacitors were in series. Now we shall name this as Cp, subscript P, and the same battery is connected here. The potential difference across the terminals of the battery is V. So V volt, V volt, V volt. Okay. So when I write this for write the expression for or the voltages or potential difference across C2 and C1, I can write V1 potential difference across C1 is equal to V. Okay. And similarly V2, the potential difference across C2, this one will also be V itself, and when we come for the effective one, there also it is V. Okay. So Vp, the potential difference across the effective capacitor, Vp. So this is what is Vp, which is again equal to V itself. Okay. In the previous derivation, Q remains same. When it comes to series, Q remains same in all capacitors, but here V remains same in both the capacitors chosen. Now Q will not be the same in both the capacitors. Okay. Unlike the previous derivation, here we will have different amount of charge stored in individual capacitors, because V is same but they have different C's, different capacitance. So obviously C is dependent on Q, or I can say Q is dependent on C. So the amount of charge stored in these capacitors will be different. So now let me say Q2 is the charge stored in the capacitor C2 and Q1 is the charge stored in the capacitor C1. Okay. Now let me say Q is the net charge stored in capacitor Cp, the effective capacitance. Okay. Now you see, let me, okay, Q1, Q2 and Q, or I can say that is actually QP effective. No, I can directly take that as Q, or if this is QP, I can write Q1, Q2 and QP, okay, QP. Now you see here, when we connect this battery is capable of pulling, assume that this is capable of pulling randomly, I am saying 10 electrons. Let us assume 10 electrons it has the ability to pull 10 electrons and push it to the other end, so that this capacitor gets charged to a certain amount of charge, QP. Now this very same battery is connected here, okay. Even now this battery has the ability to pull 10 electrons, that is it. It cannot pull more than that, okay. So out of those 10, say 6 are pulled from this, then 4 are pulled from this. Following? So it is about the ability of the battery. So these two are the same batteries. Potential difference decides what kind of batteries are there. So they are same, since they have the same potential difference. V is same, so the batteries are also same. Now this battery is capable of pulling, say 10 electrons. So that capacity will not change. If it is capable of pulling 10, it will pull 10 itself, nothing more than that, okay. Even in the previous case, if it is capable of pulling 10, it will pull 10, okay. Here also it is capable of pulling 10. So it pulls 10 from this. When you have an effective one, so it pulls 10 from this and pushes them. So this capacitor becomes charged. But now we have two capacitors connected in parallel. So this battery now has the opportunity to pull electrons both from C1 and C2, right. So if say it pulls 6 electrons from C2, then 4 of them left out will be pulled from C1, okay. 6 from here, 4 from here, then they are pushed, okay. They come and pushed here. How? This equal amount of charge should be pushed here. So if it is pulled 6 from this, 6 will be pushed here and 4 will be pushed here. Following? That is how it works. So there the quantity which is conserved here is the amount of charge, okay. So I can say the net charge in the effective one, okay, the net charge pulled QP is equal to Q1 plus Q2, right. QP, the net charge QP is equal to Q1 plus Q2. Following? Because it's about the ability of the battery. Now you think of the series connection. Let me give you the conceptual clarity. When you have series connection, there, see, this is how the series connection was. So say the battery was able to pull 10 electrons. So it pulled 10 electrons from this and pushed it the other side. That's it, right? And same thing happened with this. Pulled 10, pushed 10 to the other side. Because now it has the battery had only one opportunity to pull the electrons from this end, right? But here it has two capacitors, so it can pull from this and from this. So it will pull from both the capacitors and push them to the other side, so that both the capacitors get charged, okay. So it's about the ability of the conductor battery to pull and push the electrons. That is how you can connect things. So that makes QP is equal to Q1 plus Q2. Now think of the equations that we get when we write in terms of C1, C2 and CP. See, what we know is C is equal to Q by V, right? So C1 is equal to Q1 by V1, C2 is equal to Q2 by V2, and C3 is equal to CP is equal to QP by VP. Okay, I can simply take that as Q by V, that's also fine. Now in some reference they will give directly as Q and V, okay, that's also fine, you can take that. So what will now the factor which connects the capacitance of the effective one and the given capacitors, okay, the original capacitors and the effective capacitance are connected with the quantity charges, right, because QP is equal to Q1 plus Q2. So let me express all these equations in terms of Q1, Q2 and Qp, so that I can connect those two. So Q1 becomes equal to C1 V1 and Q2 becomes equal to C2 V2. So Qp becomes equal to Cp Vp. Okay. Now let me substitute them into this equation. So what is Qp? Qp is Cp Vp is equal to what is Q1? C1 V1, C1 plus C1 V1 plus what is Q2 here? C2 V2, C2 V2. Now from this V1 is equal to V, V2 is equal to V, Vp is equal to V. The potential difference across all of them are equal, so that I can replace them. That becomes Cpv is equal to C1V plus C2V. So now finally we arrive at the simplest equation, the final one. V is a common factor from these two. I can take them out and get it cancelled with the other V in the LHS. So V and V will get cancelled. Finally we have Cp is equal to C1 plus C2. Okay. So this is the expression for effective capacitance when we have two capacitors connected in parallel. Okay. So for series connection, it is 1 by Cs is equal to 1 by C1 plus 1 by C2. When we have parallel connection, Cp is equal to C1 plus C2. That's it, quite simple. Now this is the end of the derivation. The special case, when we have n capacitors connected in series, okay, 1, 2, 3, 4, 5, 6, 7, 8, n capacitors connected in series, then the expression is quite simple. Cp is equal to C1 plus C2 plus C3 plus so on plus Cn. Okay, or you add all of them, you will get the net capacitance. Okay. Now if all capacitors has same capacitance, which means C1 equal to C2 equal to C3 equal to Cn, then the net capacitance for that condition, when we have all capacitors connected as equal, then the quite simple one is Cp is equal to, say it is Nc. Okay. So these two are the special cases, and here ends the derivation. Derivation starts from here and its diagrams are important. Conceptually you should keep these things in mind. The potential difference across all the terminals remains the constant because they are connected to the same wire. There is no electric device here, and even with this, this will have the same potential difference across this, the effective capacitance. But the amount of charge pulled, okay, the quantity of charge accumulated, or we can say the extent to which the capacitors are charged, how much the capacitors are charged, the value Q, that actually depends. Here it is Qp and here it is Q1 from C1 and Q2 from C2, and they are connected in a way that Qp is equal to Q1 plus Q2, right? How? Because it's about the ability of the battery to pull the electrons and push them to the other side. So here say we had the battery of ability 10 electrons to pull, which can pull 10 electrons. So this battery pulls 10. So here it pulls 6 from this and 4 from this. That depends on the capacitance that we have. So that is how the effective capacitance of two capacitors can be obtained when we have two capacitors connected in parallel, and these are the special cases of that. Now let us see what is the amount of energy stored when we charge a capacitor, right? Because whenever we charge a capacitor, we are actually storing charges there, right? But in order to store charge, we need energy, right? Or I can say we have to do external work in order to store charge, right? It's somewhat like taking a bulk of mud and keeping it to a higher potential or a higher region, right? Or to be specific, I can say here the kind of work we are doing is pulling electrons or extracting electrons from one plate and accumulating them on the other plate, which is very similar to digging a pit and keeping the mud outside. Okay, so it's the mud here is somewhat like charges. So in order to do that, the mud is same. Okay, it is just replaced. We have not created mud. It is just replaced from the ground level or from inside the pit to the outside or to the surface, right, to the higher potential. The same thing is done with the charges, but someone has to do the work now. If nobody is doing the work, okay, then you can't, the mud won't come by itself, right? It will stay there. Similarly, if you want to pull these charges and push them here, you need to do certain work. Here the work is done by the battery, okay. So what is the amount of work that we do will store in the capacitor in the form of energy, right? Because this is the universal truth. Whatever the potential, whatever the work, external work that we do will store in the capacitor or in any form, in the form of potential energy, in any form of potential energy. So here also the capacitor will have its own energy stored when we connect it to a battery and charge it. Let us see what is the potential energy stored in a capacitor. So it's this is also an important derivation. Potential energy stored in a capacitor. Right. So now, what's actually happening? Say I'm taking certain charge from one plate and sending them to the other side. Okay. So let me consider the transfer of charge here itself. Okay. So in some reference they'll give the transfer of charge occurring from this plate to this plate. Okay, that's also fine. Say this is positively charged, this is negatively charged. Okay. Physically it's electrons which are moving, that's fine, but when we interpret the same phenomena in terms of charges, I can say the negative charge is moving from this plate to this plate, or I can also say the positive charge is moving from this plate to this plate. Okay, so both of them are one and the same, the same interpretation we are doing. So, and what I'll do, okay, the same phenomena, okay, whether the positive charge is moving from this end to this end via the wire, or yeah, there won't be any charge moving between the plates. Okay, the plates are filled with dielectric, which is pure non-conductor, so the charges can't move here. But theoretically, even though they are moving across the wire, we'll assume that certain charge is moving here. So before we go into the derivation, we have to assume few things. The assumption is as follows. We'll assume that the charger is charged, it's already charged, okay, not completely, but to an extent of plus small q and minus small q. So now this capacitor is charged, but not completely, to the extent of plus q and minus q. Okay. So this is very similar to what we have done so far. The work, the potential energy stored will be equal to the net amount of work done in transferring all positive charge from this to the maximum extent it can accumulate. Following? For all the charges. So what we need to do, since I just move a bit of charge, there exists potential difference. There comes a potential difference. Next I move little more charge, the potential difference between the plates increases, right? Following? So as and when I move charge from one plate to the other plate, it's actually moving like this, but I'm just taking this as an pictorial representation. Even in the reference they assume that it's moved from this, moved here itself, that's fine. It's physically it's moving like this, okay, but it's fine, you can imagine it like this. So now certain charge is moved from this plate to this plate, that makes the development of potential difference between the plates. Then I need to do more work in order to bring the next little bulk of charge. Then I want to bring one little more charge, I need to do more work than before. So it's actually variable work that we need to do every time we bring few amount of charge. So since the work we need to do every time here is varying, okay, or I can say the effort that we need to put every time to bring the charge is varying, I am going to consider a small amount of work dW. Okay. So this is already charged to an extent of q, small q, and now I am trying to bring a small charge, very small charge dq from this negative, which is positive, the dq is positive, from this negative plate to this positive plate. Following? So now I will bring this small amount of charge from this negative plate to this positive plate. Look what happens. The amount of work that I need to do is say what I told you, this is since it's already charged, okay. So let us forget the battery, okay. The phenomenon is slowly happening. I'm not going for the actual interpretation how exactly it gets charges, because we do not have the exact idea of working of battery. Once we get to know the working of cell or battery, we'll discuss those things. But for now, it's about charging the capacitor, which is pulling the electrons from this and pushing them to the other side. So it's already charged to a small q quantity, it's already charged, and a small amount of, when we charge this to plus q and minus q, say V dash is the potential difference, okay. It's not yet completely charged, okay, not yet charged completely, it's somewhat charged to plus q and minus q. Plus q is the charge stored, we say, and when it is charged to plus q, small q, V dash is the potential difference developed between the plates, V dash, certain potential difference, say 5 nanocoulomb minus 5 nanocoulomb, and the potential difference developed is 3 volt, somewhat like that, following. Certain potential difference is developed due to this separation. So now, even with the opposition of V dash, I have to push this dq, okay. So this V dash opposes the movement, even then I have to push dq from this end to this end. For that phenomena, to push dq from negative charge plate to the positive charge plate with the opposition of potential difference V dash, because charges, it's a positive charge, okay. Positive charge always moves from positive plate to the negative plate, or I can say higher potential to the lower potential. But here I am bringing that from lower potential to the higher potential with external work, right. So that external work that I need to do is, you know, that W is equal to VQ. You go for the first derivation of this chapter, you'll find it there, or the first two derivations, you'll get it. So dW here, the little amount of work that I need to do in order to bring small charge dq from negative charge plate to the positive charge plate is given by V dash dq, because V dash is the current current will make you confused. The present potential difference between the plates, okay. V dash is the present potential difference, which can be increased when we keep on bringing the charge, okay. But the complete potential difference is the total amount of work that I need to do in order to charge this capacitor completely. Say when the capacitor charges completely, say capital Q is the total charge accumulated, okay. When it is charged completely, then capital Q is the charge accumulated, and V be the final potential difference that exists between the plates. V and capital Q are the final completely charged situation of the given capacitor. This is some intermediate situation, some Q plus small q and dq is still pushing. So this is the scenario when the potential difference is V dash. So in order to push this from dq from that end with the opposition, we are doing this small amount of work, but I need to get the expression for the total work I need to do. So the total work can be obtained by integrating these two. So the net work, or I can say the total work in charging the capacitor completely, in charging the capacitor completely means from 0 coulomb, okay, no charge initially, from 0 coulomb to the maximum value Q, okay, that is the complete work. So what I need to do, I need to integrate this expression. So its integral of dw is equal to integral of V dash dq. Now which is the variable? Q, the charge, and this dq, the charge Q is varying from 0 because it starts from 0. The charging starts from 0 coulomb and ends when the complete charging is done, which is capital Q coulomb. Following? And let me put because since V dash can't be integrated here, I'll take the expression of connecting V dash small q and capacitance of the capacitor, okay. So which is the regular expression, C is equal to Q by V now. So here the C remains the same, capacitance will not change, okay. It's the physical conditions which can change the capacitance. So see, we are not changing the physical conditions, the capacitance C remains same, but the charge stored in this situation is small q, and the potential difference developed in this particular situation, present situation, is V dash. So I can write V dash is equal to Q by C, right? Let me substitute V dash as Q by C. So that becomes integral of 0 to capital Q, small q by C into dq. The limits varying from 0 to capital Q, okay, because we are charging it from 0 coulomb to capital Q coulomb. So integral of dw is W, the total work. This itself is the total work that I need to do. Now 1 by C is a constant. I'll take that out. What remains inside the integral is Q dq. Integral of Q dq is equal to 1 by C remains there. Okay, integral of Q dq. Okay, it's integral of x dx kind of one. You go for the formula, integral formula, you will get to know. If you don't get it, if you need basic integration explanation, you can text me. I'll give you the link for that. For now, it's 1 by C. Integral of Q dq is Q squared by 2. Okay. Integral of x dx is x squared by 2. Similarly, it's Q squared by 2. So now the limits varying from 0 to capital Q. Apply the upper limits first, then the lower limits. So it's 1 by C into upper limit is capital Q squared by 2 minus 0 squared by 2. This is how we apply the limits. After integration, we need to apply the limits, and after integration, in place of the variable, here comes the upper limit first, Q squared by 2 minus, and then comes the lower limit, which is 0 square by 2. This term will be 0. So finally we have the expression for the total amount of work that we need to do in order to bring the charge, the complete charge, right from 0 to capital Q, from one plate to the other plate. This is the amount of work, total amount of work, which is equal to Q squared by 2C. Okay. So this is one expression for the total work. The total amount of work that we do in order to charge the body, charge the capacitor, will be stored in the capacitor in the form of potential energy, in the form of energy, right? And that potential energy stored, okay, potential energy stored in the capacitor is same as this W. That makes U is equal to Q squared by 2C. This is one expression. What if you are not given with the total charge accumulated? Okay, here this Q is the final charge that the net charge, the total charge that the capacitor can accumulate. What if that Q is not given? If you are given with the value of V and C, the potential difference and the capacitance, then for that situation, what is Q equal to from this? The same expression carries for this. C is equal to capital Q by simply V, the net potential difference, the final potential difference and the final charge stored. From this, Q becomes equal to CV. Let me substitute CV in place of Q. That makes C squared V squared by 2C. One of the C get cancels. So that will give us the expression for potential energy in terms of capacitance and potential difference across the plates of the capacitor as half C V squared. Okay. So this is the end of the derivation. Very simple expression. The net amount of work that I have done has stored in the body, in the capacitor, in the form of potential energy, and this is the final expression of that. Clear with this? So this ends the derivation. Thank you.